So I uploaded the midterm one today, earlier today, and I revised the file, so just to make sure that you have the updated file. And I will explain some questions. I mean, briefly, look over the midterm one, and then we go to some chapter 5 lab session and also some exercises today. So I'm thinking to share my computer screen rather than iPad today because I want to show many R code today. Just a moment. Yeah. Yeah. So I think you. Can you see the midterm one?
Yes.
Okay. Okay. Great. So this is the midterm one, and we have 4 questions. And it's due on the March 1st. So basically, you have 1 week, but some materials will be covered today, and you may have some questions at the last minute. So just I would like to set the deadline on weekday. So this is an exam. So don't talk much with your friends. You can ask me clarifying questions, and yeah. Yeah, but just do by yourself, and do all questions by using R, and submit R code output and the graphics in Canvas as one PDF file, the less than 2 MB, generated by R Markdown. So last year, I think the largest submission is like only the 900 kilobyte, and this year the questions has been changed, but I expect you don't need much memory. So especially to put graphs, if you use JPEG rather than other formats such as the bitmap, or then JPEG is smaller, so usually you don't have much trouble. Yeah, anyway, then no huge data, so you may not have much concern about embedding the EPS or PostScript file. And I didn't upload it, the file yet, but I will upload a sample file for R Markdown so you can see how it works. And if you are not successful to install the R Studio, then you cannot make a R Markdown file. But in that case, you can use the Microsoft Word, but mimic the R Markdown format. So your code followed by R outputs and figures. So code without outputs and figures will not be graded. So the objective of this course is to make you be at professional level for data analysis. And if your client asks you data analysis, you cannot just submit code, right? So that's why the R output and figures are important.
Is Jupyter Notebook okay instead, or no?
You mean to
do the R in
PDF?
Jupyter Notebook with the Markdown, so it looks similar to the. Okay,
yeah,
cool.
As long as it's similar, that's fine. Yep.
Okay, thank you.
Jupyter Notebook, fine. Yes. Yeah, and yes. So as long as your final format is PDF or Microsoft Word, it's fine. And late submission will get reduced scores. So just if you are less than 24 hours late, you get the 90% of the full score. 1 to 2 days late, 60%, and other later than that, I will not grade it. And we have 4 questions. The first question is about the polynomial regression, you can see. And basically, you have to decide kind of good P, maybe optimal P. And also, the question asks you to interpret the statistical, linear model, the results, the estimated coefficients in these linear models. So the concept is that in 50-30, usually we use just linear regression, but now that we have the polynomial regression. So if you see the data, that you can see the probably you will see the some pattern which is more complicated than the linear function. And question 2 is about bootstrap, but I added one sentence just in the past hour. So the idea of this question is to code everything about bootstrap so that you can. So I can confirm that you understand the bootstrap concept. So don't use the ready-made bootstrap function, but you have to do the bootstrap basically by coding in R. Yeah, so this is a kind of coding question. And question 3 is the more applied question about linear model, but the point is that we use basically more than linear. So we include the interaction terms and the quadratic terms to fit the model, and see whether the model beyond the linear model, the linear terms are useful or not. And question 4 is the logistic regression and LDA and the nearest neighborhood method. And also it asks the some cross validation. Okay. So basically it covers linear model and the logistic regression, the LDA, KNN, and the computational methods such as cross validation and bootstrap. And cross validation and bootstrap, we will cover the methods today. Yep. Do you have any questions? Maybe some general questions about the format or how you proceed? Yeah, you have a few days, so you can ask questions on Wednesday and next Monday. Next Wednesday may be possible. Maybe it's the last minute, but also you can ask questions in office hours. Yeah. So it focuses more on the forecasting rather than more traditional statistics, since this is data science class. Yeah, so this is available in Canvas. Yep. If you don't have questions, then we go to, oh, yeah.
Sorry, Professor.
Yeah.
I have a question about our course.
Yeah.
Do we cover cross validation for other models than regression, for example, multinomial logistic regression or other models?
A good question. So I don't exactly remember all the lab sessions, but maybe not. But it's not a big problem. For example, cross validation and bootstrap. Basically, if you can solve these questions, basically you can apply the cross validation and bootstrap for other methods. So maybe we don't discuss the automatic function to do cross validation and bootstrap for other models, but you can easily do that. Yep.
Thanks, Professor.
Sure. Yeah, so when I was a graduate student, I wrote many code to do bootstrap for many other models. So it's not that hard. So just the bootstrap is just the sampling part. So as long as you sample from the original data, after that the procedure is exactly the same as usual, the regression model. So you don't really have to code the regression model itself. So you can only you can only code the bootstrap part or cross-validation part. So it's not a big issue. Okay. Yeah, so if you have questions later, you can ask me during the class or office hours, or short questions can be asked by email. Okay, so chapter 5 lab. I don't know if it's okay. So maybe I open the. Oh yeah. So lab session and some exercises, and at first lab session. So I think it's good to show just slides. Maybe just in case. Yeah, so just in case the text part. Yeah, so the chapter 5 is about the validation set approach and the cross validation and the bootstrap. So we will discuss those things. And actually in this lab session, the validation set approach and the leave one out cross validation and the k-fold cross validation. So bootstrap will be discussed in the in-class exercises file. That is also available in Canvas. Okay, so remember that the validation set approach. So validation set approach, so originally you have the data set, and we divide this into the part A and part B, so subset A and B. So B is just a complement of A. Complement B. Right. Yeah. So yeah, so at first we fit the model using this A. A is training set, and the B is the test set. So we use the training set and to estimate the model. Then we evaluate the performance with the test set. So that is the validation approach. And the division of this data set into A and B is random. So this result includes some randomness. So that is the weakness of this method. So your validation and my validation may get different result. Okay, so this is about the auto data set in ISLR library. So you can see the library ISLR, then maybe structure auto. So you have the 392 observations of 9 variables. And this is the data set basically to explain the fuel efficiency, MPG, by some other variables. Yeah, so MPG is here, and other variables are cylinder, number of cylinders, and the displacement, and the horsepower, weight, acceleration, year. The origin is the country, maybe Germany, United States, Japan, and the name. So name is the name of the car. I think the smaller data set is in original, the R package, the default R package. Yeah, you can see this. Yeah. And you can see the description by the typing help of auto. I think origin 1 to 3 is the US and Japan and Germany. Yeah, so it consists of 392 data points. So we decide to divide this into equal parts, so 196 observations each. So this is actually depends on the researcher's choice. So sometimes we put maybe 300 observation in training data set and only 92 in the test set. We have trade-off. Larger training set is better for training, but the larger test set makes the validation result the more stable. And the training set, okay, so the strategy is that we just prepare the index for training set and the index for the test set. So rather than defining just the subset of the original data set, that we just define the raw numbers. So sample 390 to 196, this code that pick 196 numbers from 1 to 392 without replacement. So each observation can only appear once or does not appear at all. So no number does appear more than once.
Professor Sam,
yeah.
Why we do like that? Because I remember that in our previous slide we did sampling with replacement, right?
Right. Yes.
So
that's a good question. So we have the two approaches. So the validation approach, cross validation is also similar ones. So this one, the objective is to separate training set and test set. So objective. So the separate training and test set. So basically we have basically no reasons to select the one observation more than once. And the bootstrap, so no replacement. Bootstrap, we do the replacement. The bootstrap, the objective is to estimate the variability of estimate. Variability of the estimated parameters. So that means for example, we have 392 observations. So when we use all observations, how much variability is in the estimated parameters? That is the question we want to answer. So for that purpose, basically, we would like to use the same number of observations as the original data set. So for example, if we have 392 observations, but we sample only 196 observations, then it's basically less accurate. So estimated parameters are not as stable as the estimates by the all observations. So that's why we want to use the same number of observations in the bootstrap. So that's why if we have 392, we would like to choose 392 out of 392. But in such a case, we don't have any variability. So we have replacement.
Okay, thank you, Professor.
Yeah. So yeah, that's the one explanation for that. And the bootstrap also is motivated by the cumulative distribution function. So suppose we have 6 observations, 1, 1, 1, 2, 2, 3. So then basically probability of 1 is equal to 1/2, probability of 2 is equal to the 1/3, and the probability of 3 is equal to 1/6. So this is the distribution, a kind of empirical distribution, and we would like to sample from empirical distribution. So given empirical distribution, possibly we pick up 1 more than 3 times, or 3 more than 1 time. So that also justifies the replacement, the sampling with replacement. Yeah. Okay. So again, the bootstrap, they want to have the same number of observations, have the same number of observations as the original set, but still want variability sample. Yeah. Okay, so now that we wanna sample it, so the point is that we sample. We just specify the row numbers. So if we type this, then we get the 196 numbers randomly from 1 to 392, and no duplications here. We cannot see at once, but it sounds that, yeah, no duplication. For example, here is 3, but the 3 is only this place, and 7 also only this. 12 also only here. Maybe next 15 or something. Maybe 17 also. Maybe I missed something, maybe 16 here. Yeah, but the no number appears twice. Yeah, and this is a plot. The this is the log scale. So original scale. So we would like to get plot. Yeah, so this is the plot. So we have some curvature here. So if we fit the data, so if we fit the regression model, probably the relationship between two variables are not linear. So the straight line is not optimal. So maybe cubic curve, or maybe quadratic curve, cubic curve, or even higher degree polynomial fits better. If we put logarithm here, maybe slightly, the situation gets slightly better, but still it's not entirely linear. Almost linear, but we have some curvature here. Okay, so now that we want to try the polynomial regression model, and we would like to determine the optimal P. So we set the regression model, CLM.1. I think the yeah, so the LM1, then we get the regression model, then we assess the test error here. So we regress the model with the training set, so subset train. So just we can specify the row index, so the which rows we will take. Then we evaluate the performance by the test set. So negative train, so this is the subset, the complement of the training set. So this is the test set. So we just calculate the difference between the actual, the MPG, and the predicted MPG, minus predicted MPG. Then this is the error size. So we take so we take the square. So we take just the test set part, then take square, then take average. So this is the basically the mean square error, test error. So that is 23.26. So if we take the square root, then that is about maybe 4.5 or 6. Maybe a little larger. So yeah, you can see the MPG, the average size of the error is 6.1 6 or 4.6 or something. So it sounds reasonable. So you can see even the we use the horsepower still. The MPG ranges from maybe 15 to the 33 or something. So we have variability. So error size, standard error of the regression is 4 point something. So that sounds reasonable. We can take square root of 23.26. So 4.8, sorry, so 4.8. So this is the standard error size. How about training error? So training error is calculated in a little tricky way. So rather than just calculating training error, that we fit the regression model with the test data set that is lm.1r. So the same model, MPG on horsepower, but we use the test set. So we use the test set, then we calculate the performance on the test set. So that means we use the same data to estimate the model and evaluate the model. So that is the training error, right? So it's a little bit complicated maybe, but the point is that so to evaluate the test error, so A is training set and B is test set. Okay. So original data. So we divide this into A and B. So D is the union of A and B. A and B are disjoint. So just D is separated into A and B, and A is training set and B is test set. Okay. Then to evaluate test training error, so we use B as the training set and B as the test set also. So the training error. So if the training set and the test error are the same, then this is the training error. Right? So in this way, that we can compare the test error and the training error the most, effectively. Right? So another way is that we use A as training set and B as the test set, but A as the test set also. But this method is not optimal because test sets are different. So we are evaluating the training error and the test error on different set. So if we use this method to evaluate training error, actually the set A is used for the evaluation, but to evaluate the test error, we used the set B as the test set. So the difference, difference gets larger. So it's good to have the same set to evaluate the model. So that's why to evaluate training error, we use the set B for both training set as test set. Okay, so because of that reason that we use this, so that we train the data with the so-called test set. Then after that, we evaluate the performance with the same set. Then the performance is, the mean square error is 22.4. So that is smaller than the test set. That is reasonable. That is reasonable. So data set has some randomness. So usually training error is smaller, but anything can happen. So if test set is really good data with very small noise, then possibly the test error is smaller than the training error. That is possible. Okay, so now that we go on to the quadratic model and the cubic model and so on. So we add more terms, to explain the MPG. So I just tried the quadratic model, cubic model, and the quartic model. So degree is 2, 3, 4. So if you use the poly function, I think this is in the default package, the POLY function, then we can define the polynomial of horsepower Yes. And we do the same thing. So this is for the training set, and this is for the test set. So we regress the 2 regressions for each P. And we evaluate the training error and the test error. And these are training error. So we use the same subset for the training and the test. And you can see that originally that was 22 point something, right? So 22.4. But if P is equal to 2, if we include the quadratic term, then 18.38. So it dramatically dropped. Then P is equal to 3, marginally better, and P is equal to 4. The very small improvement over P is equal to 3. And the training error, they usually gets small. Training error always gets smaller and smaller. So these models are estimated to minimize the the sum of squared errors, and we use the sum of squared errors to compare the models. So always a larger model has a better, smaller training error. So this is natural, but probably P is equal to 4 isn't really better than P is equal to 3. Just because we have one more free parameter, the error gets smaller. And this is the test error for P is equal to 234. Original, the error size is 23 point something, right? So 23.26. That becomes 18.716 for P is equal to 2. And P is equal to 3, 18.79. Actually, it gets slightly worse. And P is equal to 4, they're even worse. So P is equal to 2 is optimal. So see what's happening behind the scene. So this is the result for the regression with polynomial with degree 4. So this is intercept. This is the polynomial with the degree 1. And this is the degree 2, degree 3, and degree 4. Maybe these are made with diagonal, maybe. So not just x squared, x cubed, and x fourth, but probably it makes it these terms that, sorry, orthogonal, sorry, not diagonal, orthogonal. If just put x squared, x cubed, x to the fourth power, these functions are too similar for reasonable range. And also we have some very large numbers if we take the fourth power. So probably they just change the axis and so that these 4 components are orthogonal. But anyway, so this only includes the linear term. So this is the quadratic function, this is cubic function, and this is the function with degree 4. And the linear term and the quadratic terms are really significant. For example, the linear term, so we have the estimate of negative 123 and the t-value of negative 19. And the p-value is very small, less than the 10 to the power negative 15.
Sorry, Professor.
Yeah.
Could you please write the model specification, because I didn't understand the last part. You said that it does not contain the terms with 2, 3, or 4. So
yeah.
what does it
okay.
look
Yeah,
like?
I will explain that. I think I have to write the graph. Maybe I use R to explain that. Maybe yeah, just a moment. So Yeah, so the reason is that, so think about the functions, maybe just the 3 functions. So here is x and here is y. And y is equal to x is this line. Right? And y is, okay, so suppose this is 1 and here is 1. And y is equal to x squared is, maybe I change the color. So this is y is equal to x squared. And x is equal to, y is equal to x cubed is like this. So sometimes these functions are too similar. Even the red one and the green one, it's too similar. And if you can imagine that if we go the x to the 4th power, 5th power, so it becomes even. Just to make sure that can you hear me?
Yes, yes.
Okay, great. So the x squared and x cubed are really close each other. But if we use different function, then it becomes better. For example, the y is equal to x, we keep it as is. But suppose that we have this kind of quadratic function. It's much different from y is equal to, I would say, the f2 over x. So this is much different from y is equal to x. And also the cubic function, if you use this kind of cubic function, so I would say this is y is equal to f3 over x. Then, it's easily, distinguish the green line and red line. So that means if we fit some model, for example, original data is like complicated shape as like this, and we fit the y is equal to beta naught plus beta 1x plus beta 2 f2 of x, beta 3 f3 of x, then it can easily, it's better to identify these parameters. Okay. So it's easier to identify these parameters. On the left-hand side, it's difficult to estimate the model y is equal to beta 1, beta 1, beta naught, beta 1x, beta 2x square, beta cube x cube plus epsilon. So this is the reason that we use the orthogonal basis. So the red one and the green one are really hard to distinguish. So that makes the standard error of beta 2 and beta 3 larger. So this is a multi-collinearity. But here, on the right-hand side, it's easier to distinguish red curve and the green curve. So that means it's easier to distinguish the parameter beta 2 and beta 3.
Thank you, Professor.
Sure. But still, the x is the linear term and f2 of x is quadratic term, and the f cube is the cubic term. So you can still interpret this as the linear, quadratic, cubic, and the quartic curves. Yeah, and here you can see that if we fit the polynomial with degree 4, the linear term and the quadratic terms are really significant, but beyond that, it's not really significant. The cubic term is almost useless in this model, and the 4th degree, the x to the 4th power, basically, so the 4th degree polynomial, 4th degree polynomial has slightly significant, maybe t-value, the negative 1.64. It's not bad, but it's not as good as just p is equal to 2. So basically, we have the 2 additional parameters, the 2 quadratic curves, but the one parameter is almost useless, and the another parameter not really sure if it's useful or not. So it's actually, it performs worse than the p is equal to 2. So with validation approach, the p is equal to 2 is optimal, but it really depends on the set seed. So actually, if we use different random number set seed 2, then actually the p is equal to 5, even 5 is better than 4. So it really depends on the randomization. So to avoid randomization, we can use the leave one out cross validation. So we exclude one observation each time, then estimate the model with the other n-1 observations, then estimate the test error with that one observation. And we repeat that for all observations. So n times, we run the regression model n times, then we can calculate the error size. That does not have any randomness, so it's good. And the cv.glm function in the boot library, they can do the cross validation. In the midterm, I ask you to not use, but we can do the cross validation automatically with this function. And library boot and the glm function. So the point is that to do cross validation, the object should be the GLM object. So GLM is generalized linear model, and the default is linear model. So if we put the GLM and just put no options, then this is the same as LM. Output is almost identical as LM, but this CVGLM function only works on GLM. So you have to use GLM here. And okay, so this is the model. Just to put the all data set and fit the model, that is the GLM1. And just put this model, then this data set, then they can do cross validation automatically. So it's convenient. And basically the result have the two numbers, and so just you can see the first one is the usual, the MSE. So second one is a little bit corrected. So suppose we have 392 observations, then the leave one out cross validation use only 391 observation as a training set. So training set is slightly smaller. So that means the error is expected to be a little larger. So we adjust that factor. So that is this part. So it becomes slightly smaller than this. But yeah, just the first one, you can use it. This is the simple, the MSE, row MSE. Cross validation. Yeah. So it runs the regression 392 times. So it takes some time. In my old computer, still it takes less than 1 minute. So probably it's pretty fast in your computer also. So yeah. Then we want to do this for I is equal to 1 to 10. So we do cross validation for usual linear model, but we want to run this for p is equal to 2, 3, 4, and so on. Polynomial regression, we want to do that. And I use the for loop for that. So polynomial with degree 1 to degree 10. Yeah. And certainly the poly function that works better. I have seen the handwritten graphs, but if we just put the horsepower to the 10th power, sometimes the numbers blow up. If the horsepower ranges from 0 to 200, then 200 to the power 10, that becomes too large. So always it's good to use the orthogonal basis so that it does not blow up. And yeah, then each time we calculate the cross-validated error and report it. And p is equal to 1, that this is the cross-validated error size. So this is almost the same as the previous test error. Test error was 23 point something. So now 24.23, slightly larger, but the cross validation probably it's more accurate. And p is equal to 2, 3, 4, 5, 6, 7, 8, 9, 10. So we run 392 regressions each time. So in total, we run 3,920 regressions. So it takes time, but still less than 1 minute in total in my computer. And you can, what is the smallest number here? P is equal to 7. This is the smallest one. The difference between P is equal to 2, 3, 4, 5, 6, 7, 8, 9, 10. These are very small. Probably 10 is not good, but maybe between 2 and 9, they're almost the same number. Maybe 7 is slightly smaller than others. So P is equal to 7. Maybe some people prefer P is equal to 2 still because it's small enough. Sometimes cross-validation still gives too large P practically. So as long as this is close enough to this, the people sometimes accept the smaller P. But logically we have to use the P is equal to 7. Yep. So do you have any questions? Yeah, but it takes so much time. So this is just a linear model for 392 observations. So it's fine to run regression 392 times. But in general, the k-fold cross-validation with smaller k is much faster. So we do 10-fold cross-validation here. So you can specify the k is equal to 10. Without specifying anything, they do leave one out cross-validation. So that is optimal way, but it takes too much time. K is equal to 10. That means that we divide the original data set into 10 data set and drop 1 and use remaining 9 as the training set. And we repeat that 10 times. So only that 10 regression it runs. Leave one out cross-validation, we run 392 regressions, but the k is equal to 10. So that is 39.2 times faster. And this is the cross-validated error. And you can see these numbers are very similar to these numbers. For example, P is equal to 1, that this becomes this, but the difference is negligible. Next one, they're very similar. And still, the P is equal to 7 achieves the smallest, the cross-validated error. So we save a lot of time, so 40 times faster, and still the result is the same. And if our data is larger, the sample size is larger, the difference gets even larger. So it's much more efficient. Yeah, and the cross-validation, but the k-fold cross-validation, the 10-fold cross-validation divides the data into 10 pieces at random. So if we do the same procedure again, the result is different. So that is a weakness, kind of. But you can see that the result is somewhat stable. 19.28 becomes 19.14. So not very small difference, but it does not really affect the result. Still, the P is equal to 7 achieves the smallest cross-validated error. Okay. So just to replicate the same result, I put the set seed. So we use the random seed of 1 and random seed of 2. So this number should be integer. So if you put 1.1, probably the result is the same as 1. So we have to use 1, 2, 3, 4, or 222, or some integer. Okay, so this is the cross-validation. Do you have questions?
Sorry, Professor. Set that seed, what is function doing?
Set seed function. If you specify set seed, then we always get the same randomization. Let me see. For example, the R norm function, this is a random number, standard random number. Okay, so 0.27. If we run the same code that we have, you are seeing the screen, right? Yeah. Okay. So, yeah. So we have different number each time. But suppose we set seed 1 and R norm. Set seed 1 R norm. We got the same answer here. So to replicate the same result, you have to set seed beforehand. So this is lecture notes. So I would like to replicate the same number again and again. Actually, for example, here. Yeah, so p is equal to 2 is optimal, right? So p is equal to 2 is optimal for training set. But if we change the seed, then the result is different. So if we didn't specify set seed 1, then the following result will be different. So that's why I want to set seed.
Thank you, Professor.
Sure. Other questions? Maybe a little more. So set seed 1, R norm 2. Then the second number is a new one. But again, the set seed 1 and R norm 2, different. Right? Or set seed 1 and random number, 2 random numbers, 2 random numbers. Okay, so still the different numbers we get. But once again, if we set seed 1, first 2 random numbers are negative 0.62 and 0.18. Then next 2 numbers are negative 0.83 and 1.59. So we get the same numbers. Okay, and the sampling function, the same thing. So set seed 1 and sample maybe 5 from 1 to 10. Sorry, sample 5, the other way around. Yeah. Then set seed 1, then sample, then sorry, the set seed 1 sample, then we get the same number. Okay. And set seed 2, then we have different randomization. Yep. Okay, so next. Next, I would like to do exercises. I think it will be used for the midterm. So for in class, actually I ask students to do that by themselves. Then after 30 minutes, I do calculation. But okay, so here the data set D8 includes 100 observations. Oh, sorry, I think that I did not upload this data set to the to Canvas. So I will do it. Yeah, so now it's available in Canvas. So we want to do the same thing, but the cross validation. Yeah, so it's similar to the lecture note, but we have a slightly different version. So dataset D8 includes 100 observations of points X, Y. This is so similar. This is so similar. Sorry, maybe we start with question 2. So maybe if we have enough time, then we go back to question 1. I think the question 1 is almost the same as the chapter 5 lab. And for stock market data, so remember the stock market data, we predict whether the market, I mean, stock price goes up or goes down on each day. So we want to do a logistic regression. Yeah. So, but if we use the 2000 to 2005, 2001 to 2004 data as training set and 2005 as the test set, the accuracy is 58.2%. That sounds too high. Stock price is usually unpredictable. So I would like to double check this by tenfold cross validation. Yeah, so we fit the direction of the stock market either up or down. Up is 1, down is 0 on the lag 1 and lag 2. So this is the last 2 days the stock market return as basically the change in percentage. Maybe the difference of the log price. So that is lag 1 and lag 2. And so the direction on the stock market return in the past day and the 2 days ago. And the data is the S market data and family binomial. So that runs the logistic regression. So GLM with this family is equal to binomial. So this is logistic regression by default. Then we can calculate the probability. We can calculate the predicted probability of up. That is the GLM.p probs. So we define this as the predict of this model. Then after that, we so we want to dichotomize this. So this is the predicted probability, such as 0.6 or 0.45. So more than 0.5, it's predicted as up. Less than 0.5, predicted as down. So we define the vector of down at first, then we replace down by up if probability is more than 50%. Then GLM predicted, this is either down or up, and the directions 2005, this is the actual outcome. So this is also down or up. So this is the prediction. These rows indicate prediction. So this is the outcome, actual outcome. And 35 plus 106 are correct, and the 76 plus 35, so these are incorrect. Still, we have the 30 more correct decisions than incorrect decisions. So 56% the accuracy. So not 58.2, 56%, right? 56%. Yeah, so now we want to do cross-validation, but the cross-validation, so the point is that the cross-validation calculates the mean square error. So we automatically get the mean square error for cross-validation. But here, we would like to see the correct rate to evaluate this logistic regression. So that is not the mean square error. So we would like to change that function. So at first, define the correct rate function. Then after that, we evaluate with the glm.csv function. Okay, so define a function, the correct dot rate, which gives the proportion of correct prediction. The inputs are the vectors x and y with the equal lengths. The element of x are binary, 0 or 1. So x is a vector of 0 and 1, 0, 0, 0, 1, 1, 0, 0, or something like that. And elements of y are predicted probabilities that x is equal to 1. So y is the vector such as 0.4, 0.5, 0.2, 0.7, 0.99, 0.01, and so on. And y is the correct prediction if x is equal to 1 and y is more than 0.5, or x is equal to 0 and y is less than 0.5. Okay, so we have to fit the regression model. So actually the solutions are on the website, but we have to define the correct dot rate function first to use it in the cross validation, the CVGLM function. So the correct rate is the function of x and y. Okay. And at first we have to dichotomize y. So y is probability. So if y is more than 0.5, we define it as 1. Less than 0.5, that is 0. So you can just type this. If y is less than 0.5, we get false, right? The false is 0 in R, and the true is 1. So y2 becomes the vector of 0 and 1. Then now that we can make a table, then we can get the contingency table. So contingency 2 by 2 table. Then the summation of diagonal part of table. So you can see the predicted part and this diagonal part are the correct decisions, and off diagonal parts are incorrect decisions. So the correct rate is the summation of diagonal over summation of everything. Okay. So the semicolon may not be needed. So this just clarifies this line ends here. My code is clean enough, so without this semicolon, still it works. Okay, so this is the correct rate. So for example, suppose the matrix is maybe 1, 2, 4, 8, 2 by 2. M is here. So correct rate of M, y is missing. Oh, sorry, the correct rate is, sorry. This is originally vector. So the X is, okay, so just randomly, maybe sample 0, 1, 10 replacement is true. X is this vector and Y is random vector. So random uniform, so Y. So this kind of vector. So for example, if this is 0, Y is less than 0.5, this is correct decision. 1, 0.07, this is incorrect. Y becomes 0 and rounded to 0, and X is equal to 1. So incorrect, so correct, correct, and correct also, and correct, correct, and incorrect, incorrect. So if we use the correct rate function, you get 60%. So I think that 4 incorrect ones, right? So this is incorrect, this is incorrect, correct. Yeah, these are incorrect. So 4 incorrect answers and 6 correct answers. So correct rate is 60%, right? Yeah, maybe. Yeah, so 6 correct answers and 4 incorrect answers. So the correct rate function automatically calculates the correct rate. Okay, so regress the direction on lag 1 and lag 2 as a logistic regression with the GLM function. Okay, so the direction, so we have to do this. So I think the ISLR package has already loaded. So we have the S market data already. So fit GLM. Okay, so just name this as capital GLM. So GLM function on direction on lag 1 and lag 2. Data is equal to S market, and the family is the binomial. Just make sure the summary. So you have you have seen this. So yeah, p-values are not significant, but we have negative coefficients here. Okay, so then yeah, so this is the model. then calculate the proportion of correct prediction with the tenfold the GLM. So we can use the CVGLM function for this. So maybe just we name this as CV, capital CV. So CVGLM S market and GLM.0. And the cost function is correct rate. So for linear regression, the default is the I think the mean square error. So we don't have to specify this, but this time we defined the function, and we use this as the cost function, basically objective function to calculate. And k is equal to 10. This is k-fold cross validation, so 10-fold cross validation. And not C. Oh yeah, and actually we have to load package. The cv.glm function is in a boot package. Maybe I'm not exactly sure. So you can always search on the website cv.glmr. Yeah, you can search the function on the internet. Then cv.glm function is in a boot package. So we have to load the boot package. So library boot. Your computer does have this, then install it first. Then cv.glm. Still the GLM, just the GLM. Sorry. Yeah. Then CV. Then we can get the result. The CV, maybe we can just type CV. Oh, then we have the too much results. So maybe at first check the result. So k is equal to 10. Then delta. So CV $mark the delta. Then we get the cross-validated error. Or maybe CV3 also get this. Yeah. Double bracket, then just numbers. So the cross-validated error is 0.513. So only 51.3% or 51.4% correct. So that is much lower than 56%. So in the validation set approach, we were just lucky to get 56.2%. But the more fair, the evaluation is 51.4% correct. That's still better than 50%, but it's very close to 50%. Yeah, so this is, I think, what you need in the midterm. So in logistic regression, you have to set the function to evaluate the model. For linear model, the default is MSE. So as long as you want to use MSE to evaluate the model, you don't have to define the cost function. But here, we have to define it. Yep. So that's it for today. So do you have any questions?